Fundamentals of data in healthcare. Hello, everyone. Welcome to session 2. And this is your fundamentals of data in healthcare. This is a part of our basics of healthcare AI series. And we talk about your role in healthcare AI and how can you be the human in the loop. I am Dr. Umer Khan, and I've been working in health tech, IT, and technology for over a decade now. Today, we are diving into one of the most important but often misunderstood aspects of artificial intelligence in healthcare. That is data. Now, if you yourself are a healthcare professional, a provider, then this is not just tech talk. You do this on a daily basis. This is about your clinical notes, your patient's vital signs, your hospital dashboards, all becoming the fuel of what powers healthcare systems, and that is how data is derived. Of course, we can have data from the environment, from the local events that are happening, the weather, anything else, right? But specifically, we will talk about healthcare data in this video. Before we begin, I want you to think about this. Every time that you document a patient encounter, every lab value that gets entered or generated, every radiology report that gets dictated, you are contributing to what will become training data for the next generation of healthcare AI tools. So whatever you're doing, it has a lot of importance. So let's break this down in terms that makes sense for all of us in healthcare. Just a bit about myself. I am a practicing internal medicine physician, and I've been in health tech for over a decade. I've established COVID-19 monitoring units, mobile applications, been there, done that in the healthcare field with technology. Now, why data is the lifeblood of AI? Let's start with a fundamental truth about AI. In machine learning, we talked about machine learning in the previous videos. The model learns whatever you feed it, whatever you put into it. Think of AI as a medical resident. It could be a house officer, it could be a junior doctor, whoever, right? If that resident only sees young, healthy patients during training, they're going to struggle when they encounter elderly patients with multiple comorbidities. The same principle applies to AI. If your data is messy, it is biased, it's unbalanced, your AI will be bad as well. And unlike a human resident who can adapt and learn from new experiences, an AI system basically, unfortunately, amplified the patterns and the training that you have provided it. Unless you go and spend loads of money and retrain that AI with more information. Of course, we do want to train AI with more information every so often. However, you don't want your first AI to be completely pathetic and useless. Now, let me give you a concrete medical example that illustrates this point. Imagine that you are building an AI model that predicts post-operative infections after surgeries, right? You gather data from your hospital over the past 5 years. But here's the problem. 85% of your surgical patients during these 5 years were, let's say, for example, they were young, they were relatively healthy, and they were having elective procedures. Now, you can't use this data for some sicker patients, inpatient and elderly patients. And if you now deploy this AI system, but your hospital actually serves a predominantly elderly population with multiple comorbidities, what's going to happen? The AI has learned patterns that don't apply to your actual patient population. It might actually miss infection risks that are common in elderly patients, but rare in the younger and the healthier patients. Now, this isn't a hypothetical problem. We have seen this happen in real healthcare AI deployments. And the key insights here is that AI can't fix bad data. It only amplifies it. If your training data doesn't represent your actual patient population, your AI system will perpetuate and magnify those gaps, those issues greatly. Now, this is why understanding why data is so important for healthcare professionals, that when you're documenting, make sure you're documenting properly, because that will be used in the future to train these models. You are actually the ones who understand what good, real documentation and healthcare data looks like. So I recommend that all of you, whenever you're working, that you make sure that you do a good job with documentation. Not that you don't do that already, but be extra diligent. Now, to recap this, why data is the lifeblood for AI. In AI, especially machine learning, model learns whatever you feed it. The quality of the data greatly determines the quality of your AI model, your AI output. AI models learn patterns from historical data. If that data is messy, biased, or unbalanced, so is going to be your AI. And these data quality issues compound over time in all AI systems. And we gave an example that if you are building an AI model to predict post-operative infections, and if 85% of your training data is from young, healthy adults, but your hospital sees mostly elderly patients, you are setting yourself up for clinical errors and bad recommendations by your AI model, and you will not be able to implement that, and it will not be useful for your clinical setting. Now let's talk about the two main types of data that AI systems work with in healthcare, and structured and unstructured data. Now, structured data, as the name goes, is like a well-organized filing cabinet. Everything has a place in the filing cabinet, right? Everything has a place in that filing cabinet, and it's easy to find, and you can easily find what you're looking for. In healthcare, this includes things such as vitals. They are listed, they are tabulated. You can find them appropriately in the data in the EMR. Lab values, for example, medication dosages, diagnosis codes, they are clearly structured. So once you enter a blood pressure reading, let's say of 140 by 90, that is again structured data. Now, the beauty of structured data is that it's immediately usable by AI systems. The computer knows that 140 by 90 represents systolic and a diastolic blood pressure, and it can easily compare that to a normal range or track trends over time. Now, unstructured data, on the other hand, is like a conversation. It's rich with information, but it's mostly not organized in a predictable way. This includes clinical notes, for example, discharge summaries, radiology reports, procedure notes, and even things like patient voice messages or surgical videos. These are all unstructured pieces of data. So when you write, patient appears anxious and reports feeling short of breath, this is unstructured data. It contains valuable information, of course, valuable clinical information, but the computer has to work much harder to understand what it actually means. And here is what's fascinating. Most of the richest clinical information in healthcare is unstructured data. Now, lab results might be 95% structured, but doctors' notes are about 80% unstructured. And medical imaging is almost entirely unstructured because one image is, you could say, is always much different from a different image, and it could be so many things else happening in that single image. This creates both a challenge and an opportunity. The challenge is that unstructured data is harder for AI to process. That's the challenge. The opportunity is that there's a wealth of clinical insight locked into that unstructured data that AI just beginning to tap into with these models these days. Now think about your own clinical documentation. When you write that the patient looks unwell or appears to be in distress, you are capturing clinical intuition that's incredibly valuable but difficult to quantify. Modern AI systems are getting better at understanding this type of nuanced clinical language. And now to recap so that we clearly understand this, so structured data is neatly organized like an Excel sheet. Examples: age, blood pressure, BMI, lab values, hospital length of stay, medical diagnosis, ICD-10 codes, example WBC 12.5, temperature of 101, right? Unstructured data, on the other hand, is messy, it's free text, it could be multimedia, doctor's notes, discharge summaries, radiology scans and reports, surgical videos, pathology images, patient voice messages, everything. But of course, these are all fairly important. Clinical example would include patient is febrile and looks unwell, as we discussed. But the key insight is, this is, as we discussed already, this is the richest clinical data. It is unstructured, making it challenging, but valuable for your needs, valuable for AI applications. And lab results, as we discussed, is structured. Doctor's notes is unstructured. Now I want to go over this fascinating diagram. This shows us two critical insights about healthcare data evolving from 2013 till 2020. First, notice that there is a dramatic growth in the volume of data. You can see here, the volume of data here was 4.4 zettabytes. Now it's 44 zettabytes. Well, not now, in 2020, and it has exponentially increased even much further. This massive blue circle represents the total size of the digital universe for healthcare. This is a tenfold increase in just 7 years. But here's what's really important for us in healthcare. Now look at the composition of all the data that is in this 44 zettabytes of data. It could be different types. It could be notes. It could be audio, video, images. It could be medical devices. It could be pumps, monitors. It could be wearables. It could be EHR data, lab results. And you can see from this note over here that up to 90% of this data is unstructured. All of this is unstructured. This means that in healthcare, we are sitting on an enormous treasure trove of clinical insights locked away in unstructured formats. Your clinical notes, radiology reports, pathology descriptions, and patient communications, they all represent the vastness and the majority of healthcare data. But until recently, we couldn't effectively analyze it at scale and actually get real information out of this. You can see over the years, useful data is also increased. Data from mobile devices is also increased. Data from embedded systems is also increased. This is exactly why understanding how AI processes unstructured data, and we're going to talk all about that, and we're going to show and demonstrate this, and we understand that this is so crucial in healthcare. Now, the biggest opportunities in healthcare in AI are in the small slice of the structured data that we talked about. It is about unlocking the clinical wisdom embedded in the massive volume of unstructured information that you and I create every single day. Now, so how does AI actually make sense of all of this healthcare data? The process is different depending on whether you are dealing with structured or unstructured information. And I think we talked briefly about that in the last video, but let's talk a little bit more. In structured data, the features, the individual pieces of information that matter are clearly defined. The AI knows that heart rate, blood pressure, temperature are separate. They're separate measurable variables. It can analyze relationships between these values and patient outcomes relatively straightforwardly. They can say, okay, high heart rate, okay, that's bad outcome. High blood pressure, okay, relatively straightforward, high blood pressure is bad. Temperature high, straightforward, that's an infection happening, right? But with unstructured data, AI has to first figure out what features matter before it can actually analyze them. Now, this is where natural language processing comes in. Now, we all know about ChatGPT and natural language processing, but this is about healthcare. And this is how natural language processing will be used within healthcare. And I'm going to have dedicated videos on how we can actually do it ourselves, implement this, and make our models and what we need to learn about those models. Dear all, I hope you are doing great and that you are liking these lessons and you are enjoying and you are learning. And I did want to suggest something as an option for you, only if you are one of those who want to have this content in a more organized manner. There is a program that I have set up that you can find in the description. It absolutely is not necessary. However, it is only for those who do thrive in an organized approach, and there just might be a few more goodies there as well. Anyways, I wanted to share this, and now back to the video. Now, let me give you an example. Suppose you feed an AI system thousands of history and physical notes. That is when the patient is admitted to the hospital, right? For example, along with information about which patients ended up in the ICU. So over time, what will happen is that the AI learns that certain phrases correlate with an ICU admission. Oh, the patient is toxic. The patient's blood pressure is low, perhaps. The patient is somnolent. The patient is confused. The patient is not responding. All of these terms come into the mix. It might also learn terms like altered mental status, the respiratory rate is greater than 30, or the patient is tachycardic. These are all predictive signs of deterioration, that the patient is getting worse. So the AI isn't just looking for these exact phrases, it's learning the clinical concepts that they represent. Now, AI will correlate these terms and these terminologies with ICU transfer or ICU admission, right? Let's say, for example, in medical imaging, The process is even more sophisticated. Deep learning models, and we talked about that previously. So, deep learning models don't just see pixels, they learn to recognize patterns that indicate disease. A model might learn that a hazy patch in the lower lung fields might suggest pneumonia, or that certain patterns in a mammogram might indicate malignancy versus being benign. So, what's remarkable is that these AI systems sometimes identify patterns that even experienced clinicians might miss, or they may be in too much of a rush to actually look at that in detail. And a few things that a human may miss, they can detect subtle changes in imaging or finding combinations of clinical factors that sometimes humans cannot predict clearly. But AI may be able to pick that out much more quicker. But here's the crucial point, of course. AI systems are only as good as the data that they are trained on and the clinical expertise that is derived from the data that guides this development. This is why being the human in the loop, your understanding of how AI processes healthcare data is so important, and why a model will fail in your clinical setting or it has the likelihood of succeeding and actually being valuable in your clinical setting. Now, to recap how AI understands healthcare data, AI processes healthcare data differently depending on its structure and format. Now, the structured data. In structured databases like lab values or vital signs, the features are clearly defined. The AI can directly analyze the relationships between these values and outcomes. However, for unstructured data, with unstructured data, such as clinical notes, AI must first identify what features matter before it can analyze them. Clinical example, as we discussed, large language models analyze thousands of history and physical notes, and they learn terms like altered mental status, respiratory rate, tachycardia, and they correlate with, let's say, for example, an ICU admission. Now, in imaging, on the other hand, deep learning models don't just see pixels. They learn that a hazy patch in the lower lung might represent pneumonia. Now, how do we get healthcare data, and how do we prepare data to be used to train AI models? Now, it goes through an extensive preparation process, as you would have understood from the previous bit of information, that the data needs to be good. So, understanding this process helps you appreciate both the power and the limitations of healthcare AI. First, there's data collection. This might come from public data sets like the Mimic 3, and which is a large, freely available database. And another example is PhysioNet, which I believe was prepared by the NIH. And these are anonymized collections of ICU data used for research. Or it might come from your hospital's own electronic health records or your PACS system for images. So increasingly, we are also seeing data from wearable devices, ventilator logs, because all of these are being connected with Internet of Things, where data can be extracted from all types of machines, and then even such as infusion pumps, IV drips, everything. And I think I gave an example of these things in the previous lesson. So next comes pre-processing. This is like preparing ingredients before cooking. For structured data, this might mean normalizing vital signs, for example, and I'm going to just show it to you right now how this is done. So let's say converting all pulse, heart rate measurements from a standardized scale to a normalized scale. I'm going to show this to you right now. For example, mapping a pulse rate from 30 to 150 beats per minute to a scale of 0 to 1. Now, this is exactly how the computer is going to look at it. Now, if you look over here, this is your heart rate, 30 and 150. Now, when you normalize it, you have 0 over here, and you have the one whole number, 100%, 1 over here. Now, between these values, you may have, let's say, 75, right? So let's say 75 will be 0.5. Below that will be 0.2. Then over here, it goes 0.75. So this is called normalization. Now, for unstructured data, such as clinical notes, the pre-processing involves natural language processing techniques that convert text into numerical vectors that AI can work with. This is where the computer learns that SOB and assurance of breath refer to the same clinical concept. So this is where natural language processing comes into the mix. For medical imaging, perhaps, the pre-processing might involve having radiologists annotate or label images, marking regions of interest or confirming the diagnosis. Or this is pneumonia, this is where you see it. This is a nodule, this is where you see it. So that's what radiologists will do. Now, then there's a crucial step of bias checking. Now, this is where we ask hard questions about the data. Is your data set, and we can ask these questions to any vendor who is bringing in a product, is your data 80% male patients? Is it 90% white patients? Are certain conditions overrepresented or underrepresented compared to your actual patient population? So you have to know, hey, your patients are, let's say, 50% female, 50% male, but this vendor's AI is being trained on 80% male data, then of course that won't work. Because if the answer is yes, that their model is not ready for you, then your AI will reflect those biases unless you actively correct them. And this isn't just a technical problem, this is a patient safety and a health equity issue. Now, finally, there's labeling. As we talked about before, that labeling is the outcome. Pneumonia, right? Pneumonia is an outcome. Lung nodule, that is an outcome. So labeling, which means that telling the AI what outcomes you want it to predict. For a sepsis prediction model, you might label patients based on the SOFA score, the SOFA scores, or the specific ICD-10 codes. For imaging studies, radiologists might mark regions that show the pathology. Now, interestingly enough, new AI tools like the large language models we have these days can actually help in labeling in this labeling process. They can automatically identify relevant clinical concepts in unstructured notes and make this task much quicker and much faster to get your pre-processing ready for eventual use. And the key point here is that data preparation is basically where clinical expertise becomes absolutely essential. This is where subject matter experts come into the picture. And the point to note is that you cannot properly prepare healthcare data for AI without understanding the clinical context and the real world implications of the decisions that the AI will make. So getting this right in this first step is hugely important. Now, to recap so that we understand this, data collection could be public databases, private, your own EHR, or from devices, wearables, ventilator logs, etc. Now, pre-processing is very important. You need to do normalized values, and we gave an example right over here. You have to convert nodes into numerical vectors. Down the line, we'll talk about that, how to do that. Annotate imaging with a radiologist's input. Of course, you have to check for bias. Don't think of this as anything else, anything political. This needs to be done, otherwise your AI will not be effective. If your data set is 80% male and 90% white, is that your representative population or is it not? So are certain conditions over or underrepresented? If yes, your AI will reflect that unless you correct it for this problem. Now, labeling is important. Labeling means that you have to accurately label the outcome. Let's say for sepsis prediction, label patients based on scores. For imaging, radiologists mark regions of interest. And tools like ChatGPT can help pre-label unstructured notes. I have this chart here that if you have biased data sampling, biased cleaning and processing, biased labeling, and you train the model, you will get biased AI outcomes, and we don't want that. Now I want to talk about the most dangerous misconceptions in healthcare AI, and that is the illusion of high accuracy percentages automatically mean good performance, meaning that the product is saying that, hey, I have the highest accuracy. That does not necessarily mean that you are actually treating the patients properly and your performance is good. Let's say someone shows you an AI model that has 80% accuracy in predicting patient outcomes. That's pretty good, right? But here's the problem. If 80% of your patients are stable and only 20% are at risk of complications, a model would achieve 80% accuracy by simply predicting that every patient will be stable. Now, look at this again. This is very important. If the AI model was trained on, let's say, healthy patients, stable patients, and your clinical practice in your hospital, let's say 50% are actually serious and sick patients, then this AI model will not be good for you. And although on its own data set, this AI model performs well, however, this AI model will not perform well in your hospital, in your clinical setting. That is very important to understand. And as the human in the loop, these are the very questions that you will be looking at, and you will be looking at the data from the vendor, and you will be looking at your own data. Hey, does that product actually represent my clinical scenarios? And this model would be completely useless for identifying patients who actually needed interventions, but it would still show impressive accuracy statistics. But your outcomes at the end of the day will not be good. In healthcare, this kind of false confidence can be deadly. False negatives, meaning missing patients who actually are at risk or have the problem. And this can literally cost lives. And a 1% miss rate in cancer screening might sound small, but this represents thousands of missed diagnoses across a large population. Now, that is a different conversation that you see that, okay, what is the miss rate of cancer screening by a human, perhaps, right? The human miss rate might be, let's say, 2% or 3%. And somebody will argue that if an AI is bringing in a 1% miss rate, that is better than a 2% miss rate or a 3% miss rate. But of course, this has to be seen with every specific situation. And that again is where you, the human in the loop, will come into the picture to evaluate these models. And that is precisely why we need to look beyond simple accuracy metrics. We need to understand sensitivity and specificity, positive and negative predictive values, and most importantly, we need to understand how the model performs on the cases that matter the most. And we're going to talk all about that in this program. So think of it this way. If you are developing an AI system to identify patients at risk for sepsis, you care much more about catching every case of sepsis than you do about overall accuracy. You want to catch all those cases, right? You rather have some false alarms than miss a single case of sepsis. Now, that will be a valuable AI if it does not miss a case of sepsis. It may give a few false alarms. However, you don't want all the false alarms. You don't want all the false alarms. And that is, again, where you come in to see if this model is good for you. Too many false alarms could not be good for the clinical setting as well. As we all know, false alarms are a pain for any clinician. And as we say that AI is not replacing humans, and this is where your clinical judgment becomes essential. You understand the clinical consequences of different types of errors. You know what conditions require high sensitivity versus high specificity, and we'll define these things soon enough. You understand the trade-offs between false positives and false negatives in different clinical contexts. A false positive for one may not be as important compared to a false positive in another clinical scenario. So when vendors show up or vendors show you an AI tool with impressive accuracy, you need to ask the right questions. What was the prevalence of the condition in your training data? How does the model perform on the specific types of patients that you see here, actually? And what happens when the model is wrong? Does it pick up? Does it have any reinforcement learning installed? To recap this, the dangerous illusion of accuracy. High accuracy percentage can be dangerously misleading in healthcare. Example, say your model is 80% accurate, but 80% of your data is non-critical patients, and your patients are different. It might be learning to always predict stable patients and ignore the ones who truly need help. Now, this is the accuracy paradox. So look over here. If you do, overall accuracy is pretty good. It's pretty good, right about this mark over here. However, accuracy for critical cases is not that great, is definitely not that great. Now, in medicine, false negatives mean people die. And 1% miss rate in cancer screening is thousands of missed diagnoses. You must evaluate data balance, not just accuracy. Now, this diagram perfectly illustrates one of the most dangerous problems in healthcare AI. That is algorithmic bias due to unrepresentative training data. Now let's have a look at this. Now look at the left side. So algorithm training, notice that the training data contains a very limited range of patients types. You can see that all of these figures, we get a different color. You can see that all of these different images, they are similar looking. They all look the same. These all images look the same. This could represent training data that is predominantly from one age group, one ethnicity, or one socioeconomic background. Now, the algorithm, your model, learns patterns from this limited data set and creates what it thinks is a trained algorithm represented with this neural network pattern here in the middle. This is your trained algorithm from this data and model. See what happens during algorithm application on this right side. Now, when this algorithm encounters the real world, a more diverse patient population is there with different ages, ethnicities, and backgrounds. It struggles. Now, you can see all the different types of patients, young, old, black, white, all types of patients. Now, you are using this model for this population, and let's say you're looking to detect early Alzheimer's disease, you will have a problem. This algorithm will correctly identify some patients who match the training data. They may be labeled as early Alzheimer's disease, but look at the bottom. Patients who don't match the training data profile get misclassified as no early Alzheimer's, even when they might actually have the condition. This isn't a hypothetical problem. We've seen this happen with pulse oximeters that are less accurate on darker skins, diagnostic algorithms that are trained primarily on male patients missing conditions, similar conditions in females, and AI tools developed in academic medical centers end up failing in community hospitals because this whole scenario is different. The key message here in this example is that the training data contains a very limited range of different types of patients. And when you apply this algorithm to a broader patient population, this will cause the algorithm to classify many patients with an unfamiliar profile erroneously. This is why diverse representative training data isn't just a nice thing to have, it is important for patient safety. And this is why your clinical expertise in identifying these potential biases is absolutely essential, as you will be the human in the loop. Now, feature engineering in healthcare. So feature engineering is where the magic happens in healthcare AI, and it is also where your clinical expertise becomes most valuable. Feature engineering is the process of creating new variables from existing data to help AI models make better predictions. Now, it's like having raw ingredients and combining them in ways that make something more useful than the sum of their parts. I'm going to give you an example. In healthcare, we do this all the time, even if we don't call it feature engineering. When you calculate a BMI from height and weight, that's feature engineering. When you use creatinine and urine output to assess kidney function, that is feature engineering. When you combine heart rate, blood pressure, and vasopressor requirements to assess hemodynamic stability, that, my friends, is feature engineering. Now, the difference is that in AI, we can do this systematically across hundreds of variables and millions of patients. We can create features that capture complex clinical relationships that might be difficult for humans to track consistently on their own, being a human. For example, an AI system might create a hemodynamic instability index. This combines, let's say, for example, mean arterial pressure, heart rate, the vasopressor dose, and fluid balance in a way that predicts ICU outcomes better than any of these variables alone. And so let's say a mean blood pressure may be a variable that predicts ICU outcomes, but it is not as good when you combine it with heart rate, vasopressor dose, fluid balance. So individual variables may not be as good as all of these variables combined. Now, feature engineering might also help out in trends and monitoring trends. It might create features that capture trends over time. not just that a patient's lactate level is now, but how quickly it is rising and whether it is responding to treatment. And this is where the holy grail comes in, that it can assess over time, it can see what interventions are working, and it can analyze how to address that concern. Now, the key insight is that good feature engineering requires clinical knowledge, and you can't create meaningful clinical features without understanding the underlying physiology and the pathophysiology. That's where you, as the clinician, as the subject matter expert, and the human in the loop comes into this picture. And that is why healthcare AI development is most successful when it is a collaboration between data scientists and clinicians. The data scientists can look at all the data they want, but they still need you. So the data scientists bring technical expertise in machine learning, but the clinicians bring the domain knowledge that makes the features clinically meaningful. Now, when you are evaluating AI tools for your clinical setting, ask about the features that the model uses. Do they make clinical sense to you? Were clinicians involved in developing them? Can you understand why the model makes a prediction it does? Meaning that you can explain the results that the system is producing. So, you being the human in the loop, you need to learn much of this, and that's what we're here for in this program. Now, to recap feature engineering in healthcare. Let me get the red back because I like red. Feature engineering is where the magic happens in healthcare AI. It is the process for creating new variables from existing data to improve clinical performance. Basically, designing your own models and metrics and performance indicators. For example, BMI is a feature variable. It's from height and weight measurements. And you can get an AKI score from creatinine and urinary output. And you can have a hemodynamic instability index from mean arterial pressure, heart rate, and vasopressor use. Independently, they are good, but combined, they can lead to a new feature that is more representative. And you can create models that people have done in the past, and you could have your name published. You could have your name published. Great. Wouldn't that be? And good feature engineering requires domain expertise. This is where healthcare professionals add tremendous value in AI development. And you have the feature engineering process is raw data, you transform it, new features, better AI. Now, this is a bit more technical, but we will leave this for now. And this is a process. There's some data acquisition, signal processing, feature engineering. Of course, that helps out with the diagnosis if you want, or if you want prognosis for that particular AI. Now we will be going into terms that we will need to go in much more deeper in the future. And one of the most important concepts in AI development is the proper splitting of data for training, for validation, and for testing. Now, this might seem like a technical detail, but it has profound implications for how you can trust an AI system in your clinical practice. A standard approach is to split your data into three parts: 70% for training initial, then 20% for validation, and then 10% for testing. But understanding what happens in each phase is crucial. Now, the training data is used to teach the model patterns and relationships. This is like medical school. The model learns from examples and develops its understanding on how different factors relate to outcomes. This is just medical school you are learning through books, largely. Now, then is the validation data, and this is used during the model development process to tune parameters and prevent overfitting, meaning that it just does not only predict one basic thing, right? This is like a residency evaluation, right? You are already a resident, you are done from medical school, now you are a training doctor, right? You're testing the model's performance and adjusting its clinical, its training based on how it actually does. So, as we see in regular healthcare, hardly any patient reads like a textbook. Few patients read like a textbook. There are patients that read like a textbook, but few of them read like a textbook. And this is the validation stage. The validation will see if this model can actually deal with slightly different scenarios from your training data. Now, then we get to testing data. And this is used only once at the very end to evaluate the final model's performance. This is like your board exams or your live patient exams. Back in the day, we actually used to have live exams where the professor is monitoring us, seeing what we're doing, and that was a live exam. So this is the final assessment of whether the model is ready for real world use. Of course, after launch, there will still be changes needed. And of course, that will be a different topic. We will talk about that. Here's why all of this matters. If you use the same data for training and testing, you are essentially giving the model the answers to the test before it actually takes it, right? So the model might memorize specific cases rather than learning generalized patterns. In clinical terms, this is like a resident who memorized UWorld questions for the USMLE but fails when faced with real patients, or the resident who might do well on a practice test but cannot really apply their knowledge in real world situations. And if, let's say, for example, a resident only goes by the book, if the patient presents like the book, it says chest pain, left-sided, pressure, elephant sitting on your chest, and the resident thinks that that is the only presentation of chest pain and MI, myocardial infarction, then that resident will not do well in real life. This is called overfitting. This is one of the biggest risks in healthcare. And a model that's overfitting to its training data might perform brilliantly on the specific patients it was trained on, but fail like enormously when deployed on a different hospital or a different set of patient populations. So when you are evaluating AI tools, ask about how they were validated. Was the testing done on completely separate data? Was it tested on different hospitals or with different patient populations? How does the performance change when the model encounters patients who are different from those from which it was trained on? Now, to recap, training versus testing your model. Properly splitting your data is crucial for reliable healthcare. Now, training data, usually 70%. The validation data, usually 20%. Testing data, usually 10%. Now, train is like medical school, validation is like residency, and testing is the board exam or the practical exams that I had to go through. They're not here. They're not actually done these days, at least in the US, but that's it. Now, this is a little bit on the side notes. Now, these three charts show you different approaches to splitting your healthcare data for AI development, and understanding these differences is crucial for evaluating AI tools. So you need to ask the vendor, hey, what was your training data set? Now, let's say for the first chart right over here, it shows the most conservative approach, 80% training data and only 10% for the validation and test data. Now, this approach minimizes the data available for learning, but provides limited data for validation testing. Now, in the middle, the second one, this represents a more of a standard approach where we have 70% training data, 15% validation, and 15% testing. Now, this is often considered the gold standard because it provides enough data for robust validation during development, while still reserving sufficient data for final testing. Now, the third one shows a much more of an aggressive validation approach. Now, 60% training data, 20% validation, and 20% testing. Now, this approach is used when you're particularly concerned about overfitting, or when you are developing models that will be deployed across different patient populations. So all of these things matter. So this matters for you as a healthcare professional, because when a vendor comes in, you have to ask them these questions, because you are the physician in the loop. You are not replaced by AI. You are the person who is working with AI. If they use the first approach, meaning minimal testing data, be cautious. The model might not generalize well to your patient population. If they use the standard approach, the 70-15 and the 15 split, that's reassuring for most applications. If they used the more conservative approach, 60-20-20 split, that suggests that they were being extra careful about validation, which is good for high stakes clinical applications. So again, you know your clinical environment and you know your situation. Remember our medical school analogy. You want an AI system that didn't just memorize the textbook, meaning the training data, but was also thoroughly tested on multiple residency evaluations. at the validation stage and passed rigorous board exams and live testing before being trusted with patient care. Now, the key question to ask vendors is, what percentage of your data was held back for final testing? And was the testing done in patients similar to the type of patients that we have here in my facility, in my health network, in my town, in my country, in my universe? Now, next is very important, and people tend to think this is boring, but now let's talk about something that's absolutely critical, but often gets overlooked, and that is data governance in healthcare AI. So when you are working with patients, when you're working with patient data for AI applications, you're not just dealing with technical challenges, you are dealing with legal, ethical, and regulatory requirements that can make or break your project. First, there are regulatory frameworks such as HIPAA in the United States or GDPR in Europe, and various local regulations and institutional policies, maybe in your own institution. Now, these aren't just bureaucratic hurdles, they are essential protections for patient privacy and rights. They have to be there. And of course, we can talk about the pros and cons of each and every aspect. However, they are still important. This means you need to anonymize patient identifiers. That means the patient's names, their dates, medical record numbers, and any other information that could be used to identify specific patients. You need to respect patients' rights to have their data deleted and they're not coming into the final data set. You need to implement appropriate consent processes. You also need secure storage solutions. This isn't just about putting data on a server, it's about encrypted databases, access controls, audit trials, and compliance with healthcare specific security standards. Solutions such as AWS, Health Lake, or Azure HL7 are designed specifically for healthcare data with these requirements in mind. But here is the crucial point. If your AI project violates these principles, this is not innovation. This is litigation. This is litigation waiting to happen. And we have seen healthcare organizations face massive fines and legal consequences for mishandling patient data. Guys, this is serious stuff. And more importantly, these requirements exist to protect patients. And when patients trust you with their healthcare information, they're trusting that you will be using it responsibly and protect their privacy. This is another area where your clinical perspective is essential. You understand the sensitivity of healthcare information. You know what patients expect. And when they share their medical history with you, you know what to do with it. You can help ensure that AI development respects these expectations and maintains the trust that's fundamental to healthcare. So when you are evaluating AI vendors, ask hard questions about data governance. How do they handle patient privacy? What security measures do they have in place? Are they compliant with relevant regulation? Can they actually demonstrate their commitment to responsible data use? A quick recap: data governance in healthcare. When handling patient data for AI, you must follow strict regulatory requirements. Different frameworks, privacy requirements are there. Make sure you follow them. Storage, secure storage is very important. Again, as we talked about, if your AI project violates these principles, it's not innovation, this is litigation. I put this in here as a handy patient example. You have patient names, you have date of birth, you have different diagnoses, so you have images. So you have to de-identify data so that it does not get into the final data. My dear friends, I hope you're loving this. I put a lot of heart and soul into these sessions. These how you can be the human in the loop in healthcare. This content is free, and for my efforts, I want to request if you can share this with a quick message that you are loving this or that you are learning so much. Share it and send me a message, and I will personally comment below your share to send you a warm note of thanks. I would humbly appreciate you. Thank you so much. Now, how does this matter to you? Now, let me be direct with you. Whether you are a nurse, a pharmacist, an administrator, or CEO, your role in healthcare is becoming more data driven every single day. Understanding AI and data isn't optional anymore. It's essential for your career and for providing the best possible patient care. Now, if you are the type of executive who just looks at trends, oh, we did this and this happened and this improved, that, my friend, is repeated over and over again in every single hospital that I know of and I've worked and experienced. And that is an absolute wrong way of seeing if something worked or not. Of course, we will be talking about that in this course. And let's say you are in a clinical role. You're going to be asked to evaluate new tools, new AI tools to affect patient care and decisions. You might be asked whether an AI powered early warning system makes sense for your hospital or your unit, or whether a new diagnostic AI tool should be integrated into your workflow. You will be asked this question. Then you need to know these metrics. You need to know how to evaluate and how to ask the right questions whenever a vendor comes along. And in general, if you have an administrative role, you need to assess AI vendors and make strategic decisions about implementation. You will be responsible for ensuring that AI tools actually improve outcomes and don't create new risks or inefficiencies into your own system. If you are in a leadership role, you are making strategic decisions about AI adoption, governance, and further investment for your health network. You need to understand not just what AI can do, but what it cannot do and how to implement it responsibly. Now, here's the key insight. You don't need to build AI models from scratch. I will teach you in the program how to do some of that, but you do need to ask the right questions when vendors pitch you their tools, or when your hospital wants to deploy the new predictive dashboard. You need to know a bit about this. Questions such as, what data was this trained on? How does it perform on patients like ours? And you need to know how to generate the information about your own patients. And for example, what happens when the system goes wrong? How will this change our workflow? What are the privacy and security implications? Now, this series is designed to make sure you are on the inside of the conversations. You are the human in the loop, and not that you are just reacting to decisions that others are making. The healthcare professionals who understand AI will be the ones shaping how it is used in healthcare in your own practices. The ones who don't will find themselves adapting to systems designed by people who don't understand clinical practice. Let's say, for example, you are the clinician and admin is giving you a system to use, but it actually does not apply to your system. You need to be able to tell them in detail why this system is not useful in your clinical setting and give them real solid examples. I'm going to be talking about that in this program, but this is just some basic videos. So your clinical expertise is valuable in AI development and implementation because you understand patient care in ways that data scientists and engineers don't. You know what good clinical decision making looks like. You understand the human factors that determine whether technology succeeds or fails in your AI healthcare settings. The future of AI depends on collaboration between technologists and clinicians. By understanding these fundamentals, you are positioning yourself to be an effective partner in that collaboration. Just to recap why this matters in your career, you could be a nurse, pharmacist, admin, CEO. Your role is becoming more data-driven. It could be clinical roles, it could be administrative roles, it could be leadership roles. And the key takeaway is you don't need to build models from scratch, but you do need to ask the right questions when vendors pitch you the tools. Okay, so there's so many different aspects that you will understand from this program: drug discovery, outbreak prediction, radiation therapy, data collection, imaging diagnosis. We'll create one as well ourselves, smart health records, and much more. What's next? Let's recap on what's next. What we covered: structured versus unstructured health data, how data quality impacts AI performance, data preparation and feature engineering, validation, training, validation, and tests splits. Now, data governance and regulatory requirements. What's coming up next? Model architecture, how AI thinks. We will explore different types of AI models used in healthcare and how they process information to make predictions. Don't miss it. I encourage you to share this information with your colleagues, your students, anybody else in healthcare who needs to understand these concepts. The more healthcare professionals who understand AI, the better our implementation will be and the better our patient care will be. Thank you for your attention. I'm happy to take any questions. Please let me know in the comments. Thank you so much. I'm Dr. Umer Khan. Thank you. Bye-bye.